Right, so thanks again for the opportunity to give these lectures. It's been a lot of fun here. Um, uh, so in the first three talks, I talked a lot about physics, and I thought I should talk about some actual mathematics. So today my approach is going to be a little different from the previous ones. I'm going to tell you a mathematical story, and then along the way, at various points, I'm going to try to tell you, how it corresponds to the class S stuff that we've been talking about before. But the start is going to be more or less where we left off last time. So last time we said if I study a class S theory determined by a Lie algebra and a Riemann surface, if we study it in 4 dimensions, then it has a Coulomb branch, which is the base of Hitchin's integrable system. And then I said that if I study it instead in 3D, and by 3D I mean on R3 times a circle of some finite size, then the Coulomb branch will be the whole Hitchin integrable system. In other words, moduli space of Higgs bundles. And so the mathematical story that I'm going to tell is something about the moduli space of Higgs bundles. We're going to try to describe sort of as concretely as we can the sort of geometry of this space. So let me make a quick recollection just on some facts about the moduli space of Higgs bundles. So first of all, what's a Higgs bundle? So okay, let me take a group. I'll write the group SUN. Okay. Well, SUK. So what's a Higgs bundle? A G Higgs bundle over the Riemann surface C. What is it? It's a pair, say E and phi, where E is a holomorphic rank K vector bundle over C. I guess because it's SU, I should say that the determinant is trivialized. But roughly just think of just a holomorphic rank K bundle over your Riemann surface. And phi is a global section of the endomorphisms of this bundle tensor with the canonical bundle of the curve. So locally, what you would think is that, okay, I trivialize this bundle, and then what this is just a matrix whose entries are holomorphic one forms. That's what a Higgs field is. A matrix whose entries are holomorphic one forms. Okay, but somehow globalized and put on a Riemann surface. And so Higgs bundles form a moduli space. Higgs bundles over a fixed curve. And the shape of that moduli space is what we said last time. You have the Hitchin base, which is a vector space. And then you have the full moduli space. It's a kind of complex integrable system over, okay, so here's the whole moduli space of Higgs bundles, which is what we're calling M Coulomb 3D. We could also call it M Hitchin, moduli space of Higgs bundles, fibered over the Hitchin base. What is that fibration? It's the map which takes the pair E comma phi and just remembers the characteristic polynomial of phi. So last time I described the Hitchin base as tuples of differentials, quadratic differential, cubic differential, and so on. And the idea is if you have a Higgs bundle, the Higgs field is valued in one forms. So when you look at the coefficients of its characteristic polynomial, those coefficients are naturally valued in, quadratic differentials, cubic differentials, and so on. Okay, so that's the Hitchin map. And okay, so then what's the sort of big theorem about Higgs bundles? The big theorem about Higgs bundles is that if you're given a Higgs bundle, okay, some technical conditions, so not every Higgs bundle, but a polystable Higgs bundle. um, uh, that it admits a kind of best metric. So what's called harmonic metric. So what I mean by a metric, I just mean, a Hermitian metric in every fiber of the bundle. So there's a harmonic metric. What does it mean to be a harmonic metric? So okay, metric H in E. So being harmonic means that it satisfies some partial differential equation. And write that partial differential equation, what it is you take, okay. So if you have a holomorphic bundle with a Hermitian metric, then it carries a distinguished connection that's compatible with those two structures. It's called the Chern connection. So this is the Chern connection. The Chern connection is typically not flat. So you can look at its curvature. That's what I mean by FDH here. So this curvature is some two form that's valued in endomorphisms of this bundle. And now the equation we mean by a harmonic metric in a Higgs bundle is that this curvature, not that it's zero, but that it's equal to the bracket of the Higgs field and its adjoint. Or to define the adjoint, you have to again use the harmonic metric. So the equation is that this should be zero. And yeah, so the big theorem is that you can indeed solve that equation, and you can solve it. So if the bundle is actually stable, which it usually is, then you can solve it in a unique way up to overall scale. I guess it's SU, so you could even fix the overall scale. Okay, so and a lot of the sort of, I don't know, for me, the most interesting parts of the theory about Higgs bundles somehow begin with this theorem. But this is somehow a hard PDE theorem. It's not something explicit. Okay, so what's the consequence? So why do we care about the existence of these harmonic metrics? I should try to attribute. So this, I think, should be attributed to Hitchin and Simpson. In the case without punctures, and in the case with punctures, yeah. So I should have said so here I defined Higgs bundle. I defined it to be just a holomorphic object. So my curve didn't have any marked points or anything. Of course, to connect to the things we've said about class S and to get the simple examples, we'll also want the case where the curve has punctures, and then we'll be studying vector bundles where the Higgs field will be meromorphic instead of holomorphic, and there'll be some conditions on exactly what the poles will be like. So this theorem is also supposed to be true in that setting. So then I should attribute it to well, Simpson again, the tamely ramified case, and then Bicard and Bolch. Okay. So anyway, what's the point? Why do we care about the existence of this harmonic metric? So, okay, so this is something that Michael also mentioned in his talk. So the basic reason is the following thing. So let's fix a number in C star, call it zeta. And then the cool fact is that, so I told you there's this Chern connection. Chern connection is typically not flat. But now I can do the following thing. I can take the Chern connection and improve it in such a way that it becomes flat. So what you do is you take the Chern connection, you add to it the Higgs field. So the Higgs field is a endomorphism valued one form, right? So that's the kind of thing you can add to a connection to make another connection. And so what you do, you take phi over zeta plus the original Chern connection plus phi dagger times zeta. You can take any value of zeta. So people often do this just with zeta equals to 1. But you can take any value of zeta. Now it's a little exercise. Compute the curvature of this connection, and you'll see the curvature is 0. Because the bracket of this guy and this guy cancels the curvature of this one. So this is a flat connection. It's a complex connection, but it's flat. So this one, this DH was unitary. With respect to the metric H. This one is not unitary. So its holonomy will be valued in the complex group. It will be valued in SLNC. SLKC. But it is actually flat. And then, so even more, so then we have a map. We have a map which takes the Higgs bundle and produces the corresponding flat connection. So let me write that as a map of the moduli spaces. So we have the moduli of, what did I call it? M Hitchin, moduli of Higgs bundles, to what I guess we call it the Betty space, the moduli of flat connections. So here we have a Higgs bundle, here we have a flat connection. And the corresponding map on moduli spaces is actually bijection, so diffeomorphism. On the other hand, absolutely not complex analytic, right? Here, in constructing this nabla zeta, we use phi, but we also use phi dagger. So this is not a holomorphic map. There's a natural complex structure here, a natural complex structure here, but those two complex structures are different. So call this NaH, non-abelian Hodge map with parameter zeta. Okay. Oh, I guess I should, well, okay, yeah. So for everything I said so far, I actually would not distinguish those two spaces because complex analytically, they're the same. But you're right, the way I wrote it, it looks like theorem, right? Because I'm sort of giving you a formula for the connection. I'm not giving you a formula for its monotropy data. So yeah, I should say theorem. Absolutely. Okay, so this is the non-abelian Hodge map, and this diffeomorphism is the non-abelian Hodge diffeomorphism. So it says that these two spaces, which seem very different, are actually somehow the same. Now, but not only they're the same, but they're the same in a lot of different ways. So there's this zeta parameter here available. And so another way of thinking about it is that these maps NaH zeta induce a whole pile of complex structures on this single original space. So you have the original space. Now you're identifying it diffeomorphically with this other space. You could pull back the complex structure from here to here, get a new complex structure here. And you do that for every value of zeta, you get a whole pile of complex structures. So you induce a C-star family of complex structures. I'll call them I zeta on M Hitchin. And okay, so there's kind of a C-star worth of them, I zeta. Then you have the two poles, and at the two poles you have actually the original complex structure. So M Hitchin came to us with some complex structure, and that complex structure fits into this family as I0. It's the original complex structure. And I infinity is its complex conjugate. Sorry, minus. Okay, so the moduli space of Higgs bundles acquires this kind of CP1 family of complex structures, and that's sort of one of the signs that you're dealing with a hyperkahler manifold. So a hyperkahler manifold, I mean, hyperkahler is more than just this, but part of being hyperkahler is to have this canonical family of complex structures. And so indeed, so these maps NaH zeta induce a hyperkahler structure on M Hitchin. Well, if it's hyperkahler, I should tell you the metric, right? So in particular, there's a metric. So being hyperkahler means it should have a single metric which is compatible with all of these complex structures. And we can write that metric concretely. Let's write it in terms of its Kahler form. Its I0 Kahler form is, okay, so how do you calculate this hyperkahler metric? What you do is you take, first of all, you take the Atiyah-Bott symplectic form on the moduli of flat connections. So on the moduli of flat connections, there's this canonical holomorphic symplectic form called Atiyah-Bott-Goldman. Symplectic form here. So you have some relatively concrete, simple, for example, well, we can write a formula for it. So the Atiyah-Goldman form acting on two variations of a connection is just you take the integral of the trace of those product of those two variations. So some simple explicit formula in terms of the connections. And now what you have to do to make this Hyperkahler metric is you have to take that Atiyah-Goldman form on the Dram space, and you have to pull it back to the Hitchin space using this non-abelian Hodge map at zeta equals to 1, and then take the real part. And so if you do that, you determine this this Hyperkahler metric. So in other words, the problem of kind of understanding this Hyperkahler structure on the moduli space of Higgs bundles, you can solve it if you can calculate the non-abelian Hodge map. And in fact, you only have to calculate it at one value of zeta. Okay. Okay, so now there's a question, what can we do? What can we do explicitly here? Okay. So far, no physics. We get some physics in a bit. So I want to describe a kind of conjectural scheme for solving this problem, which is motivated by the physics. But I want to describe it as concrete as I can, so I want to show it in just some very specific example. So let's introduce some baby examples. Yes. There's no parameter here. So I'm giving you the Kahler form. So to give you the metric, it's enough to give you the Kahler form in one complex structure. Well, then we'd have a more complicated. So you could, of course, so we could use any zeta here, and then we don't take the real part, but we take some combination of the. But just to write something, one simple explicit thing is this one. But that's true. Any zeta would be enough to know it at any single value of zeta. Okay. So okay. So let's specialize right away to some very baby examples. So what we'll do is we'll do Higgs bundles on CP1 with one irregular singularity. So this is this thing I talked about in the previous lectures where you take the punctures, but then you collide all the punctures into just a single sort of fat puncture. So we'll do that. We'll do the most extreme version of it where you just have one irregular singularity. So this is somehow close to the context of Michael's talk. So let's fix n, but now this is different from Michael's talk. So we'll take n such that the it's coprime to k, and then so then there exists a moduli space of Higgs bundles, I'll call it MKN of Higgs bundles. Now irregular Higgs bundles over CP1, where so we put some condition on the Higgs field, and the condition that we put is that the eigenvalues of the Higgs field go like z to the k over n. Yeah, in this moduli space, they'll all automatically be stable, actually. But because it's on CP1 and because of this particular condition for the eigenvalues, yeah, it'll be stable just because there will be no sub-Higgs bundles at all. So, and inside MKN, I want to focus on so this moduli space MKN has the usual kind of shape. It's some kind of torus fibration over a base, and I'm going to look moreover, even to make my life even easier, I'm going to look just at one section, the so-called Hitchin section, so the kind of nicest, easiest part of the story. So I'm going to write down a family of Higgs bundles that just parameterizes a section of this vibration. So we'll look at the Hitchin section. Okay, so let's specialize it to k equals 2. So it's like doing the A1 theories from the previous talks. So then the Higgs bundle roughly, the underlying bundle roughly speaking is trivial. Okay, if I'm very careful, I would write it like this. I would write O of n over 4 plus O of minus n over 4. This is some parabolic structure, but roughly speaking, just think the trivial bundle and the Higgs field that you write. So now I should write a 2x2 matrix with polynomial entries, and the 2x2 matrix I'll write will be this one, where T2 of z will be some polynomial. So it'll be a polynomial which goes z to the n plus some lower degree piece, some piece of degree less than or equal to n over 2 minus 1. That's what turns out to give you a good moduli space of Higgs bundles here. And now, okay, so that's kind of the Higgs bundle side of the story. And now you ask, what's the corresponding flat connection side of the story? When we talk about the flat connections, you briefly get confused because you say, wait a minute, we're talking about flat connections over CP1 with a puncture at infinity. That's the complex plane, and so they have no kind of monodromy data, right? If you think of a flat connection as determined by its monodromy data, you would think, well, this is just completely trivial. But the story is that in the case of connections with irregular singularity, there's a more refined thing you can consider than just the monodromy. You can consider the Stokes data, which is to say, you look at, one way of saying it is that you look at the solutions of the differential equation as you go into the irregular singularity in various different directions. And each of those different directions gives you some distinguished flag in the space of solutions. And so what you get is like a point in a configuration space of flags. Let's see what it comes out to here. So if I do the non-abelian Hodge correspondence here at zeta equals 1, here in fact we'll get something we can describe. Okay, let's describe it even kind of more concretely. In this particular example, the data of the harmonic metric turns out to be the same as giving a harmonic map from the complex plane into the hyperbolic disk, whose image is an ideal polygon, an ideal n plus 2 gon. Up to SL2R action on the hyperbolic disk. So the picture is like this. You take this Higgs bundle and you apply non-abelian Hodge to it, and then it produces for you a flat connection, but you can say the data even a little more nicely. The data is really this ideal polygon. Maybe something like this. And then the kind of Stokes data associated with this is the data of these 5 points of, in general, n plus 2 points of RP1. So in other words, the practical question is, like, to calculate the non-abelian Hodge map in this case, what does it mean? It means so on one side of the non-abelian Hodge, on the Higgs side, we have the coefficients of this polynomial, which are complex numbers. And on the other side, we have the cross ratios of these n plus 2 points of RP1. And those are real numbers. So both sides have real dimension. Okay, if I have it right here, 2n minus 4. And so here the non-abelian Hodge map is a map between these complex numbers and these real numbers. Okay, so that's the setup of the problem. Calculate the non-abelian Hodge map in this kind of toy example. And now I want to describe the sort of physics-inspired prediction for how you actually calculate this map. Okay, so well, sure. I just mean the point of the configuration space. So I mean, so abstractly, there's a map between polynomials and points of the configuration space. And so, but to say it more concretely, I say cross ratios. Yeah. That's right. Well, actually, but okay, but that's a good moment to say something. So one of the important aspects of this story is that the physics prediction is going to pick out some very particular cross ratios. So it says, in order to calculate this, you should not just try to pick a random cross ratio. You should pick some very specific one, and that one will be the correct one to calculate. So yeah, okay, so let me try to describe that. Yeah, I mean, the harmonic map, I mean, so I said that in non-abelian Hodge, the thing you produce is a, yeah, that's right. Okay. So what are the predictions? Okay, so again, I'll say k equals 2. So this is the case, in the context of our class S story. This is the most baby case. This is the case where the Lie algebra is A1. And suppose I want to calculate the polygon corresponding to, say, this specific polynomial. What do I have to do? So the claim is you have to use the following set of data. So the first thing you have to use is you have to take this quadratic differential and you have to draw its what's called critical graph. So what's that? Okay, so what do? I look in the complex plane, the z-plane. So here's the z-plane. I mark the zeros of this quadratic differential. The zeros of the quadratic differential. And then from each zero, I draw 3 trajectories emanating. So what's the meaning of the trajectories? The trajectories they're the lines along which this quantity is imaginary. You take the square root of P2, you integrate it starting from here, and you get some number which generally is some complex number, but on some arcs it'll be pure imaginary. Those are called the trajectories of the quadratic differential. So we just make this picture. Okay. And so the trajectories end at 5 points, and those 5 points are somehow related to these are the regions that are going to be mapped to the 5 vertices of the polygon. So label them by the vertices of the polygon. So that's one thing we need is this critical graph. And this critical graph Okay, maybe already here we should say what's the, okay, so I promised to say where these objects arise in physics. So let's say a tiny bit about where this object would arise in physics. So just a remark, the arcs of the critical graph correspond to some particles with what physicists call BPS solitons in the theory of surface defect. So two-dimensional surface defect living inside this class S theory. So the lines of this graph have something to do with particles. The specific particles that they are, they're not particles in the 4D theory itself, but rather they're particles in the in kind of coupled two-dimensional, four-dimensional system, where you take the 4D theory and you add a surface defect, and the moduli space of that surface defect is the Riemann surface itself. And so the existence of this particle, so we have a surface defect whose modulus is this red point here. And as we move this red point around, sometimes a supersymmetric particle appears in the theory. And at the moment when that particle appears, we draw this line. Okay, anyway, this is the definition of it, but the sort of physics reason for considering it is this. It is the same, okay, good. So it is the same picture that you would draw if you were doing the so-called exact WKB analysis of the differential equation nabla zeta that we wrote here. It's exactly the same picture, that's right. But anyway, the physics meaning of it somehow is this. But that's right, it's the same picture that you would draw in exact WKB. Okay, so that's the first piece of data that you need, is you need this critical graph. The second piece of data that you need is the thing we already talked about, the periods, these period functions which controlled the Seiberg-Witten geometry last time. So concretely here, they're given by this formula where gamma is in the first homology. In this case, it's literally the first homology of the spectral curve. The spectral curve, I remind you, is given by this equation. So here it's literally just a polynomial equation, y squared plus z cubed plus 1 is 0. And so, to be really concrete, we could let's fix a basis of cycles, call them the A and B cycle. Here's the A cycle, and here's the B cycle. These are two cycles on the double cover because they enclose an even number of branch points, so they close up to themselves. And so these periods then are some concrete, explicit, complex numbers. You can even write them. So ZA, for example, is minus 2.524 plus about 1.457 I. Just to make, okay, so there's some explicit numbers. Yeah, just the integral of square root of P2 over these two cycles. So it's some hypergeometric function, but in this case, it equals that. Okay, fine. And then the last thing that we need, maybe the most interesting ingredient that we need, is so their physics meaning. So I told you last time that the Seiberg-Witten solution of the infrared gauge theory, the main quantity that appears in that solution is these periods. I can say one other thing about them. So one other remark about these periods. I'll make the remark in a second. Let's first introduce the third ingredient. So the third ingredient is we need to make a list of all, I'll define this in a second, saddle connections. Of the quadratic differential P2 dz squared. What's a saddle connection? By definition, a saddle connection is a trajectory which emanates from one zero and actually runs straight into another zero. Okay, evidently there's none here, right? All the trajectories just go to infinity. But now we do the following thing. We say, okay, I'll also allow myself to multiply this quadratic differential by a phase. So as I adjust that phase, this picture rotates. So these trajectories rotate this way. So one of them comes out like this. This one rotates this way. And at some critical values of the phase, it actually will happen that there's a trajectory that runs straight from one zero into another. And so we just record a list of every time that happens. No, it's always, oh, well, okay. If k had not been 2, we would have had much more data in the story. Right. So I'm saying if k were not 2, we would have to change many things. Because we would have not just a quadratic differential, but we'd have a cubic differential, a quartic differential, and so on. But then indeed, we would rescale. Yeah, I suppose the generalization would be we would rescale pk to e to the ki theta pk. So it is. But then we would have to have a much longer discussion because the picture we would draw would be the spectral network instead of just the critical graph. Okay. But yeah, so we make a list of all the saddle connections. So in this case, what are all the saddle connections? It'll turn out that there are only 3 of them. And there's one that goes like this. There's one that goes like this. It's kind of what you would guess. There's just the most obvious 3 making a triangle. There's nothing else. This is a question you can ask in general. So we'll encode that. And we'll sort of record this in a function from the first homology to z. Why first homology? Because for every one of these saddle connections, I can consider its lift. And that lift gives me a homology class, which I kind of attach to that saddle connection. So this saddle connection is kind of in homology class A. This saddle connection is in homology class B. And so my function omega will have omega of gamma A will be 1. Omega of gamma B will be 1. And then this third one is gamma A plus gamma B. So that one will be 1. I didn't tell you the orientation, and in fact, it turns out both of them contribute. So we'll put plus or minus, plus or minus, plus or minus. And then all other omega of gamma equals 0. So this omega, this is not a homomorphism. This is just a function on the lattice. It's supported just at 6 points, and all the other values are 0. So that's this count of saddle connections. And now, again, we should make a remark. So these saddle connections are one of the most interesting objects in the story from physics point of view. So omega of gamma is a count of what physicists would call BPS states in the theory S of G and C. So each of these saddle connections is representing some particle. So now it's a physical particle. Now no surface defect. To explain these, I had to talk about a surface defect, and it was complicated. But here, we just talk about a physical particle. The property of being BPS, what it means is that their mass is exactly equal to the absolute value of the corresponding period. So generally, there's BPS bound, which says that the mass of every particle has to be at least, if a particle of charge gamma, its mass has to be at least equal to the absolute value. It's a kind of calibration condition. Here, we're in a very special situation. These are particles which have the lowest possible mass. So for that reason, they're very stable. It's hard for them to decay into something else. So they're these kind of somehow precious objects in the story. One of the questions you want to be able to answer, if someone gives you a quantum field theory, well, you want to answer a lot of questions, but one question which is hard but also accessible is, what are all the, you want to know all the particles, but at least you could ask, what are all the BPS particles in the theory? And so in these theories of class S, there's a very nice answer, which is you just have to count the corresponding saddle connections. For type A1. And for higher A, there's a more complicated story involving some webs of trajectories. But there's also an answer. Okay, fine. So So now we're going to describe the answer to this non-abelian Hodge problem conjecturally in terms of just these data. So just the critical graph plus the periods plus these integers. Well, non-abelian here, I mean, yeah, the non-abelian here is coming from the fact that at the very beginning of this business, we said something about SL2 Higgs bundles. So the 2 is showing up in various places in the story. Yeah, that's right. That's right. That's right. Just 3 BPS particles in this story. That's very often you'll have infinitely many, but in this very simple case, you just have this finite set of them. Okay, so now I can tell you what's the sort of predicted answer to the non-abelian Hodge problem. So right. I mean, in some sense, right. I guess that's another thing that I should say. That's right. This data, right. And all of this data somehow has to do not with the original curve, but somehow with the spectral curve. So we're sort of moving things up to the spectral curve. Right. In other words, in physics terms, we're describing it in terms of the infrared data. We're going to give the answer using only the infrared data, the low energy data. And so the claim is that all you need is the infrared data that Seiberg and Witten already wrote down, plus one more thing, which is the BPS particles. And once you know that, that's enough to determine the non-abelian Hodge map. Anyway, that's the conjecture. So to state the conjecture, I'm going to give you a formula for some cross ratios. So which cross ratios are they? So I'll call them XA and XB. The cross ratios. So XA will be the cross ratio of vertices. Okay, we've got the vertices numbered there. So vertices 1, 2, 3, 5. If you look at gamma A and kind of look at all the trajectories that emanate from the 2 points in gamma A, you'll see 1, 2, 3, 5. Not 4, right? That one's not connected to gamma A. And then another cross ratio, XB, will be R 1, 3, 4, 5, omitting 2, which is not connected to gamma B on the picture. So this is some procedure for taking the critical graph, and just using the critical graph, you determine some distinguished cross ratios. So let's say, okay, maybe say a word about that. So distinguished cross ratios. And those distinguished cross ratios were determined ultimately by the polynomial P2. In other words, determined by the point U in the Coulomb branch, in the 4D Coulomb branch. So in general, the kind of picture that you get is, so this is a picture of the Coulomb branch in this example. So the Coulomb branch will get divided up into chambers. Some picture like this. Some chamber decomposition of the Coulomb branch. In each region, we have some distinguished choice of cross ratios, some kind of best coordinates to use. But the best coordinates change as you move from one region to another. So here, this is actually a picture of the Coulomb branch, the 4D Coulomb branch. But we're using it to study the 3D Coulomb branch. But this picture is literally, in this case, M Coulomb is literally one-dimensional, and this is literally a picture of it. So again, in terms of physics, so where does this, where do these distinguished cross ratios come from? They come ultimately from studying low energy line defects. So line defects in the dimensionally reduced theory. Okay, maybe I don't try to say more about that. There's some distinguished basis of line defects in the theory in each chamber. Okay, for now, let's not say more. Okay, so now what's the prediction? So the prediction, it comes in a few kind of strengths. So let's see. I want to keep all the data on the board. Okay, maybe I erase this one. Yeah. So P2, right? So in the particular case that we're studying, the polynomials P2 are of the form z cubed plus let's see. Yeah, there's a parameter here that I set to 0. So actually they're just z cubed plus u. And then we picked a particular one. We picked u equals 1. But in general, you have some Coulomb branch, and I just generically use u to mean a point on the Coulomb branch. Yeah, but in this case, it meant specifically this. So we do. So I mean, we're asking the question how to compute the non-abelian Hodge at a particular place, right? So the image of a particular point. So then we choose some particular value of u. And indeed, as we move around in the moduli space, this picture will change its topology, and so we'll get that chamber structure that I drew somewhere. You can do it at any generic u. That's right. That's right. You shouldn't do it at the. You mean u equals -1? It's not special. It's just that I wanted to draw a concrete picture. I didn't want to say, yeah. I just wanted to draw one specific one and say exactly what all the data is exactly at that one. But u equals 1 is not better than any other u. Okay, so now what's the prediction? So the conjecture. So the weakest version of the conjecture is the following. So the weakest version is something about what happens asymptotically as you go to infinity in the moduli space. And the easiest way to describe it is actually to rescale the whole polynomial. And then ask what happens with the cross ratios. And the statement is that the cross ratios go like this. They decay exponentially with this parameter r. You can think of this r, if you're thinking of the physics, you should think of r as the radius of that circle which we compactified on. And imagine taking the circle to be very, very long. So then the formula is like this. It says that the cross ratio decays exponentially with r, with this coefficient. And this correction goes to 0 as r goes to infinity. So essentially it says that e to the minus something times r. What is this coefficient? This coefficient is 2 times the real part of one of the period ZA. And if I did XB, I would write the same thing with ZB here. So in other words, so it says that if you want to study the non-abelian Hodge map and you want to study it kind of asymptotically near infinity, all you need to know is the periods, but you also have to know which cross ratios to calculate. So there's some specific cross ratios that have simple exponential decay controlled by the periods. The way you read them out is to use this spectral network. In other words, to use the decomposition of line defects into simple line defects. And then you get a conjecture here. Let me write the slightly sharper predictions. So this one did not use the BPS particles at all. So the statement is that as you go to infinity, or as you make the radius of the circle bigger and bigger, so this is a picture of R3 times S1. The statement is that as you make the radius of the circle bigger and bigger, the effect of the BPS particles is less and less. In quantum field theory, you would say, well, I'm looking at some instanton effect where the particle goes all the way around. The particle has to go all the way around this loop. That effect will be suppressed by e to the minus r times the mass of the particle. And so as r goes to infinity, that should be more and more suppressed. And so in that limit, we only use the periods. We don't use anything else. Yeah. So I could have if I put b here, it'll be b here. Yeah. How can you understand them explicitly? Oh, you mean what is a cross ratio? Yeah. So we said we have 5 points of CP1, 5 points of RP1. So the data that comes out of non-abelian Hodge is going to be this polygon in RP1. And so it has a bunch of points, say 1, 2, 3, 4, 5. And then the cross ratio. So which cross ratio did we say? It's like 1, 2, 3, 5. So think of, label these points by real numbers. Right? This is RP1, so think of 5 real numbers. Then it'll be like x1 minus x2, x3 minus x5, divided by x2 minus x3, x5 minus x1. And I should say the fact that this thing is governed by real numbers and not complex numbers has to do with the fact that we took zeta equals to 1. So in general, in this business, you get complex connections. You would get complex numbers here. But just accidentally, because we take this thing on the H section and because we take zeta equals to 1, we're living on kind of a real slice of that picture. Yes? Right. So if you try to write the cross ratio for A plus B, so that'll be some combination, right? Because this moduli space is two-dimensional, you can express that cross ratio as some combination of XA and XB. In general, not just additive. So I mean, there's this Plucker relation. There's some formula that tells you how to write the cross ratios. Yeah, I should be able to instantly write the formula for you, but I can't. It'll be something like, XA times 1 minus XB, some combinations like that. It'll be some Laurent polynomial in XA and XB. That's what you can generally say. Right. So yeah, so I said it in terms of the harmonic map, but in terms of a flat connection, the picture would be that we're studying some SL2C connection in the plane. We're studying an SL2C connection in the plane. And then let's draw a picture here. So it's an SL2C connection with irregular singularity at infinity. So in that situation, you have 5, okay, with the asymptotic that we chose here, you have these 5 distinguished directions for going to infinity. In each of those directions, this flat connection, think of a flat connection as like a differential equation. It has a unique solution that decays as you go in this direction, a unique solution that decays in this direction, and so on. 5 distinguished solutions. If you take a generic solution, it exponentially blows up. But there's 5 special ones that decay in these 5 different directions. Well, the space of solutions itself is two-dimensional, right? Because it's an order 2 differential equation. So what you have is inside of C2, you have 5 distinguished, well, I said 5 distinguished solutions, but they're only determined up to scale. So we have 5 lines in C2, call them L1 up to L5. Well, 5 lines, another way of saying that is that you have 5 points of CP1. Call them X1 up to X5. 5 points of CP1. So when you have a flat irregular connection in the plane of this kind, it determines for you 5 points of CP1. Then you take the cross ratios of those 5 points, and that's what we're talking about. I said it in the language of the harmonic maps just because I think it's a prettier picture somehow, but maybe I shouldn't have. They're essentially the entries of the Stokes matrices, yeah. They're simply related to the entries of the Stokes matrix. Okay, so right. So then in general, those would be complex numbers, but for the particular connection we're studying here, they happen to be real numbers. Okay. So then let me say, I probably won't get to say the strongest prediction, but let's say the kind of middle prediction. So because that already uses these BPS particles. Well, the prediction was something sharper. So the prediction is this. Well, okay, so this is a conjecture, which you could attempt to, I mean, you could prove it or not, right? Has this been proved? I think that some closely related things have been proved. I think this has not exactly been proved, but sure enough, you can check it on the computer, and it's true. I mean, okay, it seems to be true. Okay, so then a slightly stronger prediction is the following. It's a formula for this correction. So I said there's some error, but I didn't say what the error is. So the conjecture is that the error is given by some explicit formula. So right, so this is what I said before. So but another way of writing it, which is maybe more evocative, is that it's a sum over all the BPS particles. So the idea is that the correction, as I said, is coming from the BPS particles. And you can write it in that form as a sum over these BPS indices. Okay, and the actual formula is a little bit complicated, but just to show you that it's some explicit formula. So this is this exponential suppression factor that I was talking about here. I guess I forgot about a factor of 2. So for some reason, in my normalization, the mass is 2 times the central charge. Where now this one goes to 0 even faster. So the statement is, in other words, you can calculate the non-abelian Hodge map near infinity. Its leading behavior is exponential and controlled by this spectral network picture. The first subleading term is then an exponential down from that exponential. So the error here is exponentially small. And it's determined by the BPS particles. Then there's yet a stronger prediction, which is supposed to determine this function exactly as the solution of some integral equation. And that integral equation, again, is determined just from this data, just from the kind of infrared data of the theory. So the remarkable thing is that these BPS particles, so studying the BPS particles and line defects in this n equals 2 theory seems to be enough to describe the non-abelian Hodge map. Okay, I emphasize it's absolutely a conjecture. But in this particular case, it's very well numerically tested because you can actually solve the PDE. So Hitchin's PDE in general, it's hard to solve. But in this particular case, you can actually solve it on a computer. And then you can compare it to this prediction, and you can compare it to the solution of this integral equation, and the thing seems to actually work. Okay, that by the way, that verification is in some joint work of mine with Emily Dumas. And the broader prediction is part of my kind of older work with David Gaiotto and Greg Moore. The class S story, of course, depends on the work of many people. Okay, some of whom I mentioned along the way. Okay, maybe that's a reasonable place to stop.